Welcome back to our discussion of moles. We're going to expand on the previous topics a bit now, and we're going to talk about not just converting between a number of grams and a number of moles like we did here on the previous video. Now we're going to expand that to discuss going from a number of atoms to a number of moles, and then from a number of moles to a number of grams. So we're going to go through all three of these different ways of describing a sample. Now, if we're trying to go from atoms to moles, or sorry, from atoms to grams, there's no direct way to do that. There is not, and by direct way I mean there's not a single conversion factor that can do that. You will always need to convert to moles first, using Avogadro's number, and then use the molar mass to convert that number of moles into a number of grams. And so the pathway is going to look something like this, where there's no direct way to go from here, a number of molecules or atoms, to a mass which would normally be in grams. There's no direct way to do that. Instead, you're going to use Avogadro's number to go to a number of moles, and then use the molar mass from the periodic table to figure out how many grams you have. Now, likewise, you're going to follow the exact same pathway, just in reverse, to go from grams to a number of atoms. It just depends on what you're trying to do. And throughout this course, we're going to go back and forth and only go through one of these conversions here. It just depends on what we're trying to do. All it depends on is what our goal is, where we're starting and where we're going. So sometimes maybe we'll just go back and forth here. Sometimes maybe we'll just go back and forth here. We don't have to go through both of the conversions if we don't need to. But these two things here, Avogadro's number and molar mass, this is what we're going to use to go back and forth into moles and out of moles, either from atoms or grams. So let's look at an example of this. So this says, how many aluminum atoms are in an aluminum can with a mass of 16.2 grams? So let me see, I don't have space there. I think I have enough space here to work this out. So we're starting with 16.2 grams of aluminum. So we're starting here with grams, and we're asked to figure out how many atoms of aluminum are in that sample. So we're trying to go to here. So we're going to go through these two conversions to get there. We're going to use the molar mass to go from grams to moles, and then we're going to use Avogadro's number to go from moles to atoms. Now the molar mass of aluminum, if I remember correctly, is 27, but let me check real quick. Yeah, essentially 27. 26.98. So for every 26.98 grams of aluminum, I will have 1 mole of aluminum. So that is the molar mass, again, directly from the periodic table. So that is the first step here, but I'm not done yet. I need to then use the second conversion factor, which is Avogadro's number, to figure out how many atoms that would be. And Avogadro's number is the same for everything. So if we have 1 mole of aluminum, we would have 6.022 times 10 to the 23rd. In this case, this would be atoms of aluminum. Now, if we were doing this with a molecule instead of an element, it would just be that number of molecules instead of that number of atoms. All right. Let's see, where did I put my calculator? There it is. So, if I go ahead and do the math here, grams of aluminum cancels moles of aluminum cancels, leaving me with atoms of aluminum. So 16.2 divided by 26.98 times 6.022 times 10 to the 23rd. That is going to give me a very large number, which is 3.62, we'll say, times 10 to the 23rd atoms of aluminum. All right. I hope that made sense. Let's look at a couple conceptual checkpoints here. So that page number, I'm not 100% sure is correct in the newest version of the book. That might be from an older version, but hopefully the question itself has not changed. The conceptual checkpoint has not changed. Okay. Let me see if I can find that here. Where did that end up? There we go. Okay, so conceptual checkpoint 6.1. Actually, let's do 6.2 and 6.3 instead. 6.1 is actually going to take us back a little bit, at least in the edition of the book that I have here at my house. I have the 5th edition here, so it's actually not the newest edition. But regardless, the questions are still good here. So 6.2 says, which statement is always true for samples of atomic elements, regardless of the type of element present in the sample? So which of these is always going to be true, no matter which element you're looking at? So option A is if two samples of different elements contain the same number of atoms, they contain the same number of moles. B, if two samples of different elements have the same mass, they contain the same number of moles. Or C, if two samples of different elements have the same mass, they contain the same number of atoms. Now I know there is a lot in those there, so what I would encourage you to do is pause the video or rewind the video for a few seconds, and you can hear me read through that again. One of those statements is correct, the other two are incorrect. So go ahead and rewind it if you need to, and see if you can work out which of those statements is true. If you said statement A is true, then you are correct. A was true, so just to remind you, A said if two samples of different elements contain the same number of atoms, they contain the same number of moles. That is true because moles are specifically related to the number of atoms present. Again, it's just like a dozen. If you have 24 marbles or 24 bowling balls, you still have 2 dozen of each. It doesn't care what the thing is that you're talking about. All it cares is the number of things. But the other two, that is not the case. So for part B, it said if you had the same mass, they would have the same number of moles. That is not true. And part C said if you have the same mass, they contain the same number of atoms. That's also not true, because different elements have different sizes. So the last one there, for example, if you have the same mass of bowling balls and marbles, you're not going to have the same number of bowling balls and marbles, because marbles are much smaller. So if you have the same mass of both, you must have a lot more marbles than you do bowling balls. So I hope that makes sense. So the last one here, which is 6.3 in the edition that I'm looking at, it says, without doing any calculations, determine which sample contains the most atoms. Would it be 1 gram of cobalt, 1 gram of carbon, or 1 gram of lead? So you have 1 gram of each of those things: cobalt, carbon, and lead. Why don't you pause the video for a second and see if you can figure out, of those three samples, which one has the most atoms. All right. If you said 1 gram of carbon would have the most atoms, you are correct. Carbon is the smallest out of all of those elements. Carbon has a mass of 12, cobalt has a mass of 59, and lead has a mass of 207. Carbon is the smallest, so just like our example with the bowling balls and the marbles, I guess we have three things now, so maybe we have bowling balls, baseballs, and marbles. If you're going to have 10 pounds of each of those things, you can get that with one bowling ball. You can get that with, I don't know, maybe, I really don't know what the weight of a of a baseball is. Let's say 30 baseballs. I don't know, just for argument's sake. 30 baseballs. You get you 10 pounds of baseballs. 10 pounds of marbles is probably going to take a few hundred marbles, at least, just because they're so much smaller. So these smallest atoms, you're going to need more of those to get the same mass that you would have with larger atoms. So I hope that makes sense. The idea of a mole and thinking about things in terms of the number of atoms that are present is a little bit more of an abstract way of thinking about things than we're used to at this point. But it is something that we kind of need to get in the habit of as we're going throughout the next few chapters, because we're going to be doing that more and more often. All right, I think we'll go ahead and leave it there for this one. And the next one we'll talk about applying these same principles to molecules and using chemical formulas to pull the conversion factors that are already there inherently in the molecule itself. So I'll see you there in the next video.